So this is part 2 of lesson 2, topic 2, sorting out the sorters. We're going to pick up where we left off, where we're going to talk about spanning tree protocol. So again, this goes back to the concept that we had a problem with switches, especially as they got better. And the whole point of switches is they were good at interconnecting other switches, unlike hubs, which cause more, larger collision domains. As they got more and more switches connected up, it didn't take long for some person to decide to connect a switch into the home switch, right? So we have the connection out to the network itself, right? We have a switch here. We have another switch here, bigger switch apparently, I don't know, terrible art. Connect to another switch. Ooh, it swung around here somehow. All right. And then we have another switch. And then somewhere along the way, some idiot decides to plug this into here. I shouldn't say idiot, but someone decides to plug it in here. Again, this is a problem because if someone sends a broadcast, let's just say this node sends out a broadcast. Cool, broadcast, I'm a switch, you get it, you get it. I got a broadcast, you get it, right? You don't send it out the receiving port, so you get it. But meanwhile, this guy got the broadcast on this side. I got a broadcast. You get it. 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 You end up with a broadcast storm. All right. So this became a issue. So let's figure out how we're going to solve that issue. Spanning tree protocol. I don't know when exactly it came out, but I can tell you what, when I first started configuring it back in the late 90s, early 2000s, it was very, very slow. This was some of the earlier versions. We have 802.1d, often called common spanning tree. I mean, we're talking a minute, 2 minutes to have a connection come up. There's a lot going on, and it kind of makes sense. When we look at how spanning tree works, it's going to make sense why it's taking so long. But just know, when it first came out, it was very slow, causing problems actually. IPX and was the biggest one. The drivers for IPX loaded up so quickly that IPX would give up because the port was down. It was like, oh, you're not plugged into anything. I can't forward off any traffic. So we had to work around like spanning tree port fast, which we'll talk about in a second. So Cisco quickly panicked, I shouldn't say panicked, but Cisco quickly developed a PVST Plus, which is their proprietary protocol that supports root bridge per VLAN. So yeah, we're going to talk about this, the practice. Remember, spanning tree protocol works at layer 2. It's going to be a layer 2 protocol. And because it's a layer 2 protocol, it's going to be per VLAN. So every VLAN is going to have its own, we're going to talk about root bridge, and we're going to talk about, essentially layer 2 topology, potentially have its own layer 2 topology. So things get a little complicated. But anyway, PVST Plus worked with per VLAN. It was also a little bit faster, if I remember correctly. 802.1w, rapid spanning tree, used more port walls to speed up convergence. We'll see how that works. And then Cisco has rapid PVST plus, go away, per VLAN 802.1w. Okay, so the trend here in general is we're trying to speed things up and work with VLANs a little bit better. All right. And as you probably saw, we have PVST Plus and Rapid PVST Plus running on our simulated switches. So, some important concepts. Bridge ID. This is how we're going to know what we're running. Okay, so let's go back to my. I don't need that. Let me exit out of this and go back to our demo over here. All right, let's take a look at our spanning tree protocol. This is after practice 1. So if I do show spanning tree, I've liked this. Summary was a little confusing. What was the one I did like? I liked active for some reason. I thought active looked pretty good. So if we look right here and we do spanning tree, well, actually, why don't we do summary? All right, so I'm going to do summary. All right, so here's our summary. This is the root bridge. As you see, the switch is right now in PVST mode. It's the root bridge. It's going to have, it's not really showing the bridge ID. I would like to see the bridge ID. I guess if I hit detail, I'll get it in a lot more information. and it's going to go per port here, per VLAN. Yeah, it's going to be that kind of that fun. Port 16. Let's see what's after that. Here's VLAN 6. Bridge identifier has a priority of 32,768. We're gonna deal with that right now. Okay. So span tree is not going to give you a nice little pretty picture of your topology, but bridge ID is an important concept. All right. So we're gonna have bridge ID, which essentially is your switch's identifier. Okay. Now it's going to play an important role because based off that number is how we're going to elect a root bridge. All right. So by default we have 32,768, which you saw earlier, and then we take that and we combine it with the MAC address. The lower the better for bridge priority, which is your bridge priority is how you're getting elected root bridge. Now we're going to see that root bridge plays a major role because we're going to figure out the layer 2 topology based off the root bridge. The root bridge will become the center of the network. Now, is it a huge deal if my root bridge isn't actually my center of my network? Yeah, a little bit. Depends on how complex the network is, right? But for the most part, it won't matter. If you have a simple star network, it won't make that big of a difference. But if you have enough stars off of stars and the root bridge is far enough along, or you have a kind of a very hierarchical LAN design, it can cause problems. So you might want to control what your root bridge is. And we do that in the practice. So we do control the root bridge. Again, it's going to be a combination of the bridge priority and the MAC address. Okay. Since we all start off with the same bridge priority, it's going to be whoever has the lowest value MAC address, right, to figure it out. All right, how are we going to figure this out? Well, we send these things called BPDUs, Bridge Protocol Data Unit, BPDUs, okay? They're frames, layer 2, sent out by switches to map and figure out the layer 2 network. It's like a broadcast, but it dies at layer 2, all right? Now, the important concept here is if a switch sees a BPDU, it's a layer 2 broadcast, best way, and it identifies. So if a switch sees a BPDU come in on a port, it knows, aha, I have a switch on that side. If it sees its own BPDU come back to it, then it knows it has a layer 2 routing loop. Okay, those are two important concepts, right? It's like a broadcast. It just has the sole purpose of identifying what switch sent out the original BPDU. So that way, if I see it cut back, I can go, uh-oh, we got a problem. We got a layer 2 routing loop. All right. We also have port cost. It's a rating of the quality bandwidth of the port. Again, if we're going to be setting up a layer 2 route and a layer 2 topology, and we're going to start blocking ports that are multiple ways home, we're going to want to make sure we block the crappier connection. Well, the way to make sure we block the crappier connection is we give a rating per port. So our ports are all Ethernet ports. They're going to get ratings of 100. But let's say we all set a 10 gigabit port that gets a rating of 2. Cisco kind of made a mistake here, and not twofold actually. They reduced. They went from 10. The 10 megabit port is a 100 rating. The 100 megabit port is a 20 rating, or 19 rating, excuse me. And then we went to 4. Then went to 2. 30 gigabit, I'm guessing, is 1. I haven't really looked, but they're going to run out of numbers, and it's lower is better. So there you go. That was the other mistake. They made lower better. If you do higher, numbers are infinite, so higher is better. But again, there's this trend of lower is better in some Cisco protocols. And here you go. Well, in this case, they could argue IEEE, but whatever. Anyway, path costs. So the total port costs incurred during the path to the root bridge. Right away, you can see, right, a switch, once it plugs into the network, and once we're setting up spanning tree protocol, it's going to send out these BPDUs, and they're like echoes, boom, boom, like sonar, right? They're figuring out the topology of the network. And what's going to happen is based off so it's going to designate, okay, how do I get to the root bridge, right? It's going to draw this map with the root bridge in the middle, okay? So it needs to figure out its path cost, every possible way you can get to the root bridge, okay? And then it's going to figure out how great that path is by taking up all the port costs and say, hey, what kind of port is this? Oh, it's 10 megabit? That's a score 100. Oh, you're a gigabit, 1,000, right? You're a gigabit? Oh, that's a score of 4, right? And the lower score is the best path cost. So that's why they made a lower score, path cost. They said cost, so therefore lower the cost, the better, right? All right, so some terminology. We're going to talk about ports, okay, and how these ports come into action. So we're going to designate a root port, which is the lowest cost port to the root bridge. Whatever wins, whatever has the lowest cost, that becomes my root port. Okay, it's very important. Designated port. The port with the lowest cost that gets frames to a different segment of the subnet. So we're going to have designated ports and non-designated ports, right? The non-designated port are the ports with the higher cost. So this gets me to a different segment, right? So this is going to get me to a different part, not exactly to the root bridge, because it's a designated port. What we're going to see here, let me go back to my, that's right, I'm on a different, so I'm going to shift window down. There we go. That's a smart way to get there. So again, let's go spanning tree, and I do that spanning tree active. This is why I kind of liked it before. You're going to see these are designated ports. Why are these designated ports? Well, first of all, I'm the root bridge, so that's why they're all designated ports. The quickest way to get to me is to be me. So let's actually do this one over here and do a show spanning tree active. All right. There we go. We have designated ports, and then we have an alternate designated port, and then we have the root port, right? 0, 0 is how we get back to the root bridge. Okay, we have an alternate. What's that mean, alternate? Well, we'll talk about that in a second. But if you look, 3, 3, that's how I get to switch 2. So it's another way to get to the root bridge, right? That's what it's doing. All right, and it's figuring out. Okay, this is how I get to the root bridge. This is a good highlight color, by the way. All right, that's great. I should just do that black with a lighter color in all of these. That would make more sense. All right. So all the rest of these are designated ports because nothing else is plugged into them. That's what's going on. It's a different part of the network. It's not hearing back BPDUs. It's not part of this love triangle going on over here. So it's just a designated port, right? We're not shutting it down. Its status, it's in forwarding status. We're not shutting it down. This is blocked, right? BLK is for block. Right? It's an alternate way to get to the root bridge, but because if we turn it on, it's going to cause a layer 2 routing loop, so we're going to block it. All right? That's what's going on. All right? Forwarding port. Any port that is not blocked can be designated or non-designated. We have block ports. For your own protection, we'll still listen to BPDUs only, right? So block ports aren't 100% blocked. They're not down, down, down ports. If they're a blocked port, at least spanning tree blocks them. What they're going to actually do is they will still listen for BPDUs, data units. So there you go. We have an alternate port, which I showed you, not using 802.1d. That's just a block port. So that's part of the older protocol. It didn't designate other ports to say, hey, this is an alternate port. This is a different way to get to the root bridge, right? It only works in newer bridge protocols. So what happens is if I kill this link over here, let's go back down. If I unplug this, right? Unplug this, the way back to the root bridge. For this guy, 0, 0, right, is my root. That's my root port, right? That's how I get back to my root bridge, right? If I kill that, I'm going to have to figure this out real quick. So let's just kill it. See how long it takes spanning tree to figure it out and get convergence. Convergence means we can all agree. Well, I'm hitting buttons. I don't want to start a capture. I just want to delete. There you go. So now I've killed it. Let's go back and let's check this out and see how long it takes it to figure it out. We're still forwarding, and we're still alt block here. Let's see, spanning tree, figure it out. Still forwarding. Will it help if I ping? Again, this is not the fastest thing in the world, and that's why it's not really great for using it for backup. But, so if I use ping right now, I wonder if I 168. Let's see, do it to yourself, spanning tree. .1. Oh, well, I'm ping. That's weird. 192.168.0.1. What? Oh, that's actually, well, that's fine. 192.168.0.1. Do I have a comma in there or something? What's going on? Or protocol not running. I guess VLAN 1 is dead. So, did I set a IP in this? No. Well, there's my problem. Shoot. All right. So let's go into config. Let's go into VLAN 1 and assign his IP address real quick. 168.0. We'll just make this .13. Something I didn't bother doing. IP address is the command. and I gotta put a subnet mask. 255, 255, 255.0. We'll do a no shut. Sorry about that. There we go. All right, now that we've done that, now I can start pinging things, or try to ping things. I think I'm gonna, there we go, eventually came through, so now let me see if that got spanning tree to work its magic. And 00 is designated now because, again, it's not, because it's not getting any BDPUs from there, or BPDUs, I always mix that up. It's not gonna block it, right? Because it doesn't know where it's going out. It's to a different subnet as far as it's concerned. It hasn't heard anything reflect back on it. But it does know the way to get to the root bridge now is through here, right? So now it's spanning tree has recalculated and said, oh no, my root port was lost. Let me go to this way instead. All right. Now the fun part is I'm going to have a layer 2 routing loop in a little bit here because I'm going to reconnect it. Let's have some fun. Oh, what port was it over here? It was 3.3, wasn't it? Yes. 3.3 to 0.0. There we go. Let's go back and check out the situation here. Spanning tree should be panicking a little bit because now it's seeing bridge BDPUs. Did I get that? BPDUs? I always mix the two up. I can ping. Let's see. And it automatically, it's jumped over. So good job by spanning tree right there. It jumped back over and said, okay, good. 0.0 is the quicker way to get to the root bridge, right? But this is an alternative, and I'm blocking it for now. I'm going to wait until my moment and bring it back over. So that's how spanning tree works, okay? We also have a backup port, which is also blocked to the 2.1, but for faster calculation when other switches go down. So what might actually happen if we have a really complicated network with lots of switches everywhere and lots of weird paths to get back to that root bridge, convergence is what happens when the switches all come to an agreement is, aha, this is the way we should block ports or forward ports, okay? When we all agree on what the right layer 2 path is, that's called convergence. We're also going to use it for routers. It's when routers can all of a sudden agree this is the fastest way to get from route A to route B and so forth, okay? So STP, we have different states in STP. We have disabled, which is shut disabled. So again, I might get a little surprised here how it looks in the simulator. Sometimes the simulator can have a little different results, but let's go for it. So 3.3, let me do a quick look. If I go into 3.3 and say, what's up with 3.3? 3.3 doesn't seem to be working, right? Or it's orange. If I do show int Ethernet, and I'm not expecting to have redundant connections. I didn't know about this going to another switch and that being a problem. It's going to say up, which was a surprise there. So 3.3 is coming up as up, which I don't think is what it would say in the real world. So again, this is where the simulator acts a little bit differently than the real world. Show error disabled. These are all the error disabled. So if I do BPDU Guard, I can actually turn that on. I'd see an error disabled. All right, so anyway, the important thing here is we have a disabled port. So that's like that blocked port, right? The blocking port, right? Listening. So what happens is when the switch first comes up, it can go to listening mode, okay? Listening and learning mode, okay? So what happens is listening means I'm just listening for BPDUs. Let me make sure I'm getting that right. I always need to refresh my memory. There you go. BPDUs, Bridge Protocol Data Units. All right. So again, a listening port is going to listen for BPDUs, right? Learning says, listen, I'm going to keep listening for BPDUs, but I'm going to start forward. I'm going to start listening to your frames and start building my MAC forwarding table. Okay, and then we finally have forwarding, which means it's up. It's ready to go. It's a designated port. We don't have to worry about layer 2 routing loops from this port. Okay, or it's forwarding because it's the root port. It's the root port back to the root bridge. Okay, it can also be forwarding as well. Convergence, all ports of the network are in blocking or forwarding state. So again, it's not learning, it's not listening, it's trying to not figure out the best ways. Every single port and every single switch in the network is either in a blocking or forwarding state. That's convergence. In other words, we know how we're supposed to be configured. So there's a special command called spanning tree port fast. It's going to warn you, particularly if you do it to a trunk port. It don't no likey that. But let's do it here to another port. Let's do 01. So I'm going to config T. I'm going to go int Ethernet 01, and I'm going to do, we'll go switch port access VLAN 2. We'll put on VLAN 2, and I want to just real quick. Description was. We're not going to put a description, but I want to put spanning tree port fast. So I type spanning tree, and I do port fast. Okay, there it is. I thought they didn't have it in the simulator. Spanning tree port fast. Okay. So when I hit that, it's going to give me a big warning. Don't do this unless you know for a fact it's only going to workstation. Now, we had to have spanning tree port fast. I remember this when I got deployed because a lot of early computers are really fast and coming up and booting up quickly, right? Granted, this is the 90s and 2000s. Most computers took forever in a day to boot up. We're talking about Pentium 1 computers, right? Or maybe Pentium 2. Were coming up and they were really slow. But if they came up and they beat port fast, if the computer came up before port fast or started loading up the operating system and started doing DHCP, or IPX got loaded up as a DOS driver, so before Windows even started loading, IPX would load up, and it would IPX go, the port's down. I'm going to turn myself off. The port's down, right? In other words, port fast was, spanning tree was taking so fast that we had to have a special command that says, listen, with port fast, just start, even while you're listening, even when you're learning, when you're listening, forward frames, okay? Which could be a bad thing for that. You know, especially like if we went back to the common spanning tree, the original slow one, that could be a minute or two of broadcast storms. I might be enabling broadcast storms for a minute or two on my network, right? But again, we needed to do this in order to get certain protocols working and certain machines working, fast booting machines up. All right. So the newer switches are pretty at getting the ports up. Port fast is kind of almost integrated in, so you see it less, but it's still there as an option. All right. So spanning tree port fast at the interface level, like we did, you gotta do it per interface. Puts port in a forwarding state even when it's still learning. There's another thing we have called BPDU Guard, which usually, by the way, goes with spanning tree port fast, because if I'm going to turn it on, it's going to say, you know what would be a great idea? If I see any BPDUs, I'm not going to think about it. I'm going to shut this port down. Now, I loved it as a network administrator because anytime someone plugged in a switch that was running spanning tree, it would shut down the port. I would have a port with BPDU Guard on. So I'm just trying to remember the command. Did I do that at I thought I did that at interface level. No, I'm just trying to gun my way. Is it switch port? Yeah, probably switch port. When in doubt, in an interface switch port. Nope, it's not there. Let me quickly do a little research and figure out how to turn on BPDU Guard. Give me a second. Okay, sorry. So it was under spanning tree. So spanning tree, again, I could have sat here and just kept making question marks, but so under spanning tree, in the interface, I'll do it right now. I'm in interface Ethernet 01, and then I do spanning tree. And then BPDU. Now there's two options here. There's filter and guard. We want to do guard, and we can either enable it or disable it. So we're going to enable it. And there we go. Now we got BPDU Guard enabled on this particular port, which is not connected to anything. So it does make sense anytime a user says I need a port activated to actually put that in there, because if a user gets tricky or thinks they're being tricky and unplugs that device and plugs in a switch, guess what? It's going to take down the port. Therefore, it helps you get better control of your network. It's a really good idea to put on anything you have spanning tree port fast, right? Because if I'm running port fast and I'm really worried about, okay, fine, I want this thing up as fast as possible, then my user unplugs the node and puts in a switch, BPDU Guard will shut down the port. All right, so there I was reading up on it real quick, but I just needed the command. All right. Well, there you go. Well, port fast PTP Guard default. There you go. So I had it in my notes. There you go. So spanning tree. If I do it in the config mode, I can make it the default for the ports and say all ports are doing BPDU Guard, or I can go in per interface and using the spanning tree BPDU Guard enable command I just showed you. You can do it. Well, there you go. No reason to go out to the internet. It was in my notes. This was just a quick example, but I used the simulator instead, which is much better. Let's just talk about CDP. So Cisco Discovery Protocol is it advertises a device on a network. It'll give you the device type, the model, IP address, the host name, capabilities, operating system version. We'll see that in a second, and we'll play with it slightly in practice. Device advertises every 60 seconds. It uses a multicast MAC address, which is 01000 Charlie 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 Charlie. It's a special MAC address specifically set to Cisco devices. A lot of other devices will respect that MAC address, but that MAC address is set as a special MAC address. It will push it on to multiple devices. But again, it's a layer 2, so we'll see this in the practice. It doesn't. It's directly connected devices. So CDP timer, so you can change that if you don't want to do every 60 seconds. You can do it more or less, whatever. Cisco devices keep tables of devices, flushes after 180 seconds of hearing nothing. So after 3 intervals of 60 seconds, I say, hey, I haven't heard from this guy. I'm going to just drop him. Okay. By the way, CDP hold time, you can change that as well if you don't like the 180 seconds. There's 2 versions. They are backwards compliant. Now, this is a Cisco proprietary protocol. CDP is Cisco Discovery Protocol. There is a competitor version, LLDP, Link Layer Discovery Protocol, which is an IEEE standard, so it's got probably an 802 or whatever number on it, but it's called Link Layer Discovery Protocol. So it's Cisco devices, we're pretty much all happy running CDP, and a lot of number of devices are happy to run CDP as well. So if I do show CDP, details, not details. Let me get this right. Show CDP neighbors. That's what I wanted. Neighbors. There you go. It's going to show me the 2 devices I'm connected to. Now notice, even though 3.3 is in a blocking state, it still works. CDP somehow sneaks on through. Neighbors, let's look at your details. So it's going to say, listen, I got this host name, SW1 on 162inc.com on port 00, right? And I have 162 SW2 on 3.3. That's lovely. Let me give it more details. So if I get more details, it'll tell me switch 1. It'll give me its IP address. That's awesome. That's the big thing. It'll give me the model number. Also notice, by the way, in just the summary, the neighbors, it had this code, okay? This is a switch, but it has routing capability. It can be a layer 3 device. We're not doing that right now. Excuse me. It is a switch. It is also has a IGMP, which is a routing protocol. We won't talk about that right now. But it can also act as a router. It tells me the capabilities. Ironically, the platform says Linux, and that's because this is the simulator. That's kind of fun. I haven't seen that before. It can tell me the version of what operating system I'm running. That's very cool. It tells me the version it's running of CDP. It tells me the VTP domain, right? It gives me all kinds of great information that I can use to help manage and inventory my network. Now, you might notice here, I'm on switch 3, and I'm not seeing the router. Does it not show routers? Did routers not participate? Routers do participate, but again, it's not going to do multiple hops. Whoops. So like if I go to the router and I do show CDP neighbors, it does mean neighbors, next door neighbors. I'm only going to see switch 1, as you can see right here. Switch 1. That's a terrible highlight color. I got to work on these highlight color. If I excuse me, I had to sneeze. If I need a sneeze button. If I go to switch 1 though, because switch 1's in the middle of everything, I'm going to see everything. So again, going to your core of your network and knowing where the core of your network is going to be important here, right? So if I go to switch 1, that's not switch 1. If I go to switch 1, here's switch 1. And I say, hey, switch 1, let me see your CDP. Let's just do the summary here because we're going to see lots of data. This is called forever. Show CDP neighbors. And if I just see the neighbors, I'm going to see everyone. I see switch 3, I see switch 2, and I see router 1. So a powerful tool. If you're at the core, you do it at the core, you can see everything. But anything that's 2 hops or more than 2 hops, you're not going to see. All right? So it's not much of a multicast MAC address, really. Switch stacking. Let me just talk about switch stacking real quick. So often, case in your building at STCC, building 2 has, last I saw, 7 switches. I think they're up to 8 switches in their switch stack. In other words, there are 7, in order to feed all the ports here in Building 2, this big monstrosity, American brutalism style building, 7 floors high. Yes, we should have a closet per floor, actually. That's a long story. By standards, that's what it should be. It's a stick tradition, though. We only have 1 closet per building for reasons both good and bad, which I defended in the past. Anyway, so switch stack, well, actually, I wanted to go back to this and do my drawing. Sorry, more drawings. So here's the problem. If I have a bunch of switches all piled up on each other, that's fine. I can uplink all those, and they would all have their independent connections back to the core. All these would be backbone connections, right? Let's draw 5. Okay. However, each one would have an IP address. I would have to figure out what users plugged into what switch, right? It's going to make my life logistically a bit of a problem. So if I have, even though there are 48 port switches, and by the way, the ones in Building 2 here are all 48 port switches. We have that many ports here in this building to activate. So what I can do is actually set up just one uplink to the backbone. I can set up multiple ones for redundancy and link aggregation, which we'll talk about. But right now, let's keep it simple. One link with one management IP, 192.168.0. Let's say it's Building 2.2. And then in the back, they've got these Cascade cables, or they have these data link cables in the back end. And what I can do is I can plug those in. Now, the way they're set up is they're called cascading. What does that mean? Well, it means I kind of create a loop, and it does almost spanning tree to block it. It's fascinating. So I'm going to have one link go down to here, another link go to switch 2. This is going to have a link go to switch 3. This is going to have a link go to switch 4. And this will have a link that goes down to switch 4. Right? And that way, if one of these some idiot unplugs one of these cables, I can still contact all the switches. And what this does is this turns this into one logical switch. Remember earlier I referred to an interface. I said, hey, interface, and it wasn't an accident, gig, because last time I configured the switch stack, they were gigabit ports. 1, 0, 1. What that means is switch 1, so this switch right here, port 0, port 1. Or if I wanted to go the port 16 here on the third switch, I would do gigabit 3, 0, what did I say, 15? I don't remember what I said, 15, right? And then I could configure this port, okay? By the way, when I do like show MAC address or show run, it's going to show me the configuration of the entire stack. For all logical purposes, this switch is going to be, all these switches will be one logical switch. All right, that's a true modern-day switch stack. Older switch stacks did not work that well. Every switch had its own individual config still. That's way back in the 2000s. Modern switches actually just kind of turn into one logical one. So that's a switch stack, okay? And that's how switch stack works. And they're awesome. I do recommend you doing it for logical purposes. That way I have one switch stack per building. It's easier to manage, easier for me to configure and manage. All right, different models, different approaches. All right, so switches in summary. Switches learn MAC addresses and forward frames based off their MAC address table. Also sometimes called a CAM table, particularly in the old Catalyst 6000 series. So anyway, just know that. I mean, you don't need to know that for the test, but I'm letting you know. Switches can use SDP to prevent layer 2 loops. Switches use VLANs to carry different subnets traffic on the same physical switch. Switches can use CDP to create a table of all its neighboring devices. Switches may be stacked to create one logical switch. All right. I know this was a lot of information. I hope it was worth it. I hope the practice reinforces everything we talked about. I'll be posting this and sending a link on Blackboard right now. Okay. Talk to you later. As soon as I stop the video, which is up here.